So I guess we can get started. Good afternoon, everyone. Welcome to the Physics Colloquium. And today we're very excited to have Professor Victor Tsai visiting us virtually from Brown University. So Victor received his bachelor's degree in geophysics from Caltech in 2004. And then went on to receive his PhD from Harvard University in 2009. After, I guess, 2 or 3 years of postdoc at, this is, I guess, USGS, Geological Hazard Science Center. And he became, he went back to Caltech and became a faculty member there and became a full professor in 2017. But then he moved to Brown across the continent in 2019. So Victor has worked on various subjects, I would say, in geophysics, from modeling frictions, so frictions on faults, to glacier, subglacial hydrology, tsunamis, debris flows. You'll hear some of those talked about today. But I think a continuous theme for Victor is kind of applying physics modeling to geophysical problems. And I'm not going to list some of the notable publications, but I just want to mention that Victor also received the 2012 Archie Young Science Awards. That's one of the most prestigious AGU awards. So that's the annual Geophysics Union meeting awards to sort of the outstanding young scientist. So with that, I'm gonna let Victor take over, and it's yours, Victor.
Thanks, Chinya, for that really nice introduction. And it's been a really great time visiting today, even though it's been virtual. But thanks for inviting me to give this talk. So today I'm gonna talk about applying physics, and a particular type of physics, statistical mechanics, to try to understand some Earth processes. And the ones that I'm going to concentrate on here today are on processes that cause erosion and about earthquakes. And I thought that these two pictures here would be good motivation for my talk. So these two pictures that I have here, oops, that doesn't work. Okay, here we go. The picture on the right is from the Kobe earthquake. It's damage that happened in the Kobe earthquake in 1995, and we'll come back to that in a second. And the picture on the left, some of you might notice, or some of you might recognize, that it's a picture of downtown Los Angeles, where you see all the tall skyscrapers in the foreground. And you might notice that in the background, not so far away from downtown Los Angeles, are these really big mountains. These are the San Gabriel Mountains, which are just a few kilometers away from downtown LA. The one thing that I wanted to mention about these mountains is that every year there's lots of erosion of these mountains, meaning these mountains are being eroded away. The mountains are growing at the same time, and they're also being eroded. And that every year there's approximately 10 to the 6th tons of sediments that are being eroded from the San Gabriel Mountains. And actually, maybe surprising to some of you is that these sediments are actually trucked away on trucks because we don't want those sediments getting into the populated areas of the Los Angeles region. So that implies that there's approximately 10 to the 5 trucks that need to truck away all those sediments that are being eroded from the San Gabriel Mountains. I'll get back to this question, but there's this important question of why does this erosion happen? And I'll spend part of the talk talking about this. Okay, and then on the right-hand side, this picture from the Kobe earthquake, I just wanted to emphasize here that every year there's a lot of damage that's caused by earthquakes around the world, especially or including in the United States. So actually, I don't know what the statistics would be for Canada, but in the United States, approximately $6.1 billion worth of damage is done by earthquakes every year. So this is annually. There are damage to buildings like this example from Kobe, which is in Japan, but there's similar types of examples of this type of damage happening in the United States. And so, of course, at a very large scale, then you might think that there's these earth processes that are quite important societally to people that live in various regions of the world, including in these ones that you might recognize. And I did want to focus, though, on the processes here, where if you focus now on the processes that are involved, it turns out that on the left-hand side, all this sediment that is being eroded from the mountains, the proximal cause of that erosion is that they're caused by debris flows. So there's many of these things that we call debris flows, which are basically sediments being washed down the mountain, usually in events that are related to rainstorms. So there's some rain that happens and that washes this debris that was on the mountain down the mountain. This 10 to the 6 tons of debris or sediments that are being eroded are carried by debris flows off of the San Gabriel Mountains. And so that's the process that I'm going to concentrate on for that side. And then on the earthquake side, it turns out that much of the damage that we talk about related to earthquakes is related to the strong accelerations that happen in earthquakes. And so you can think about there being multiple types of ground motions that occur during earthquakes, some of which are very slow and where the displacements may be large, but the accelerations may not be large. And other types of motions where the displacements may be relatively small, but the acceleration can be quite fast and can cause damage to these types of buildings. So that's the type of thing that I want to talk about today. And actually, I should mention that throughout this talk, I'm going to be talking about these 2 different examples. They may not seem very similar to you, at least to start out, but hopefully by the end of the talk, you'll see why I'm talking about these 2 different examples of earth processes and where they might share some common ground in the physics that describes them. Okay, so this is what I'm going to talk about today. And again, getting back to this idea of what processes we're interested in, I'm going to turn the question now to how we can understand the forces that are interacting during these debris flow events, and also in this other case, in terms of the earthquakes, in terms of what causes these ground motions that cause lots of damage in these events. So I've sort of flipped the question from one that's maybe one of societal importance to this question about the physics and trying to understand what are the underlying processes that are most important for causing the damage that you might see in these events. Okay. So the next thing that I wanted to go through was I wanted to show you some examples of what these things actually look like, because I think it's important to get a sense for what these events look like. So I'll talk about the debris flow one first, but on the right-hand side is the case about earthquakes, and on the left-hand side is this example about debris flows. And I'm going to show you this video, which is actually a very unique video that was taken for one particular debris flow that happened in Argentina, where these people happened to be hiking over this region and where a debris flow suddenly happened. So I'm going to play the movie now. And you'll see that people are just hiking along like normal. They're crossing what appears to be this very small amount of water that's flowing down. But there's this guy who warns them, and all of a sudden, you see this dramatic debris flow. And I want to emphasize there's a lot of things going on here, but there's this very complex mixture of really big boulders, a lot of mud, a lot of water, and actually there's multiple phases that occur in this debris flow. So pretty soon you'll see another phase coming where I think you'll see some more big boulders coming along. Let's see, maybe it'll be in a moment. They're now panning over to look at the people to make sure they're okay. But so there you saw another release of boulders, which shows you how complex these debris flows are. And actually, for those of you who might be wondering, it looks like a nice sunny day in this place, but actually there was precipitation happening, rain happening upstream of where these people were. And so that also tells you something about the complexity of these debris flow events. Okay, anyway, what I wanted to emphasize here was that it's actually a very complex mixture of boulders, mud, and water. And in order to understand the processes, you might think you might want to understand this very complex mixture. Okay, so that was for debris flows. For earthquakes, I just have this example here of a ground motion record. So this is how the ground was moving as a function of time. So this vertical scale is actually acceleration as a function of time during that same Kobe earthquake that I showed you the picture of earlier. And so what you notice is that the ground motion also appears to be quite complex. So there's all these peaks and troughs within the ground motion. It's not just one cycle of acceleration and then deceleration that you might have expected if you thought the process was simpler. It's this rather complex series of accelerations, decelerations, accelerations, decelerations that continues for approximately 20 seconds for the Kobe earthquake. And for different earthquakes, it lasts for a different amount of time. And so there's this question now that you might ask about whether we can try to understand these types of events where there's a significant amount of complexity in them. But before we talk about the complexity, I wanted to mention what people have worked on previous to the work that I've been doing. And so to take a step back to talk about some of the models that people have produced for trying to understand these types of events. And I'm going to go through this very quickly, but there's these sort of cartoons for how people have traditionally understood debris flows on the one side and earthquakes on the other side. These cartoons sort of simplify the physics in certain ways to an extent where we think we can understand some of the processes going on. So for debris flows on the left-hand side, you'll see that people make a sort of cartoon of how the flow is flowing downhill. And there might be a certain velocity profile to the flow that's moving downhill. And the one thing I wanted to mention about that is that these flow models that people work on have been getting better and better with time. And actually right now, I would say the state of the art for modeling these flows of debris flows, they can do a very good job explaining the average behavior of these debris flows, in that they can very well explain the velocity profile, the average velocity profile that these debris flows have. But one of the things that it doesn't do so well is it can't explain very well the time-dependent behavior, or in other words, the fluctuations away from that mean average flow. And for that reason, they also they have a difficult time explaining the damage that's created by debris flows, and also the erosion that you might be interested in if you're thinking about this from a geologic perspective in terms of how the San Gabriel Mountains, for example, are eroded by these debris flows. And then on the earthquake side, I've shown you a couple cartoons here of simple pictures of how an earthquake works, where basically people think about there being two plates where stress is loaded up, and then that stress is suddenly released, and that release of stress during a short period of time is what constitutes the earthquake, which then causes the ground motion. And there's various ways of explaining how that slip on that fault turns into waves that we then observe and can cause damage. But one of the key things I wanted to mention here is that, again, these models have been getting better and better with time. And now I would say they can explain the low frequency energy that's being produced by earthquakes relatively well. In that, for example, if you have a time series of the low frequency energy in an earthquake, the models for this sort of stick slip on a fault process happening can very well explain the low frequency ground motions. But when you try to use the same model to explain the high frequency, strong accelerations that happen in earthquakes, these models typically do not do a very good job. And so here's the question, or the dilemma here, about, well, how can we proceed? We have these relatively simple models of explaining the average behavior or the low frequency behavior of these types of events, but how can we explain this complexity of these events? And so today I'm going to talk about one approach where the question is, the broad question is, how do we explain or how do we understand these complex processes that have many, many degrees of freedom, or many, many different things moving around during the either debris flow or the earthquake? And I would say generally there are two paths forward. One which is an empirical approach, and one which is based on mechanics. And I'm not going to focus on the empirical approach, but the one thing that I'll say about that is that usually empirical models are only as good as the data that goes into it. So if you have good observations of certain events, and those observations span all the types of events that you might try to predict in the future, then empirical models seem to be, or can be very good. But one of the failures of empirical models is when the observations that you have don't span all the different types of events that you might be interested in. And so I'm going to focus really on trying to apply physics to try to understand these complex systems. And because we're talking about complex systems, statistical mechanics turns out to be a useful approach. And so I'm going to spend the rest of the time talking about how to use statistical mechanics to try to understand Earth processes, particularly debris flows and earthquakes. And just as an outline as to how the rest of this talk is going to proceed, I'm going to give you a brief history and outline of classical statistical mechanics. I'm going to try to condense a whole course's worth of material into just one slide here, where I'll talk about the key assumptions that go into statistical mechanics and the interesting results that are predicted. And then I'll talk most of the time about these applications of statistical mechanics to either debris flows or earthquakes. And hopefully you'll see that there's actually a strong relationship between how we can explain these complex motions for debris flows and earthquakes. I'll tell you about some of the main differences, both between the standard statistical mechanics approach and the applications to the debris flows and to the earthquakes. I'll talk about some of the key assumptions, and then I'll actually focus on some of the interesting results that we can predict with this model. Okay, so with no further ado, let me go on to this sort of brief one-slide summary of statistical mechanics. And I'm going to talk about an ideal gas. So the ideal gas is the sort of standard way in which statistical mechanics is usually introduced in a university statistical mechanics class. And there's this video that's playing, which shows sort of the example or the stereotypical example that's in mind, where there are many particles in a box, and each of these gas molecules, each of these particles is moving around within this box somewhat randomly, where the rules that are satisfied are that these are all identical particles and that they collide elastically with each other and with the walls of the box. And the one thing that is known about this system is the mean energy, or sometimes people would call it the temperature. So you might have a thermometer that measures the temperature of the box. You know how big the box is. And you then want to describe what is the velocity distribution of these particles. What are other things that you might want to know about these particles, and can you describe it in a statistical way? And so I'm not going to get into all the mathematics or the physics that goes into obtaining these results, but if you take this assumption, it turns out that you can derive a number of very interesting results that are related to thermodynamics. And what you have to do is basically, if you assume that the most likely scenario is the one that is observable, or is the most likely scenario given the temperature constraint is the one that, that would occur in nature, then you can derive all of the things listed here. So for example, you can derive this equation about how temperature, entropy, energy, pressure, and volume are related, which is the fundamental thermodynamics equation. And you can derive these laws of thermodynamics that typically in a traditional thermodynamics class are taken for granted or are assumed. But using statistical mechanics, you can actually derive the first, second, and third laws of thermodynamics. And very interestingly, you can also derive the ideal gas law. So PV equals nRT, maybe most of you are probably familiar with that from a high school chemistry class. You can derive this equation, PV equals nRT, from these very, very simple assumptions about random particles moving around within a box. And you can actually get even more specific information if you wanted to know about the distribution of velocities of these particles. Not only is there a mean velocity that's related to the temperature within that box, but you can also derive the distribution of velocities. And it turns out that you get this Maxwell distribution of velocities that's well known in terms of how gases behave. And that comes out of this statistical mechanics assumption. Okay, so that's my one slide summary of statistical mechanics. And now I want to tell you about how can we use this sort of framework to try to understand these other complex Earth systems. And I'm going to make an analogy here where for these Earth processes, you might also want to understand some of the statistical behavior where some of the physics might be quite similar to these particles moving around within a box. And now you have to you have to take it with a little bit of a grain of salt, but these systems might look a little bit similar to particles within a box if you look at them in the right way. And so the key assumptions we're going to think about here are that, again, we're going to have many particles, and again, they're going to be colliding with each other. Some of the differences are that now inelastic processes will become important. So unlike the molecules within a gas, which basically collide elastically, when we're talking about real materials like rocks and boulders in a debris flow, or like pieces of rock within the Earth, then there will be these inelastic deformations. And then the other thing to keep in mind is that the forcings are going to be very different. So in a gas, the thing that really forces these gas molecules to move around is that the walls are moving a little bit. And every time a gas molecule hits the wall, it gives it a little bit of energy and causes it to keep moving around. In the case of debris flows, the main thing that's providing the energy to these particles to move is gravity. So gravity and these particles wanting to move downhill to go from higher elevation to lower elevation is the main forcing. And for earthquakes, the main forcing is this tectonic stress that's being built up on these faults, which is then suddenly released. So the driving force or the driving energy is very, very different for these Earth processes compared with say, the gas or other statistical mechanics. But some of the basic mechanics or some of the basic physics, which involves particle collisions, may be similar. So for debris flows, I've shown this schematic over here where you could think about the sort of average behavior looking like this top panel. But if you look at the individual particles or the individual boulders within a debris flow, it might look a little bit like this, where of course this is idealized, but now all of these particles can move around stochastically within the flow. And one thing that you might be interested in is what is the average fluctuation in the velocities away from the mean velocities at which these debris flows are moving downhill. And then on the earthquake side, maybe it's a little bit harder to imagine why earthquakes might behave like this many particle collision model that I talked about. But one thing that is true is that if you zoom in into detail at most of these faults around the world, you will find quite a bit of complexity in these fault structures. And so here I have just one example of some of the complexity that's observed at these fault zones around the world, where you'll notice the scale bar here is 1 meter. So on the meter scale, or the tens of meter scale, and also on the hundreds of meter scale, there's significant complexity in these fault zones. So it's not just a single fault over which you're loading up and which you then allow the stress to be relieved on, which I described before, or which you might have thought of with this sort of simplistic view of what an earthquake might look like. In fact, there are all these structures within the fault zone, which you might think of as particles, which can collide with each other as the earthquake tries to release the stress. And so that's the analogy that I'm going to make. And I'm going to try to show you what some of the consequences of this analogy are. So now I'm going to get into a little bit of the details about the various types of assumptions that we can make and what kinds of things we can calculate as a result of those assumptions. So it turns out that there are different end members for assumptions that you could make about what these, how these many particle systems behave. But one of the assumptions is called what's called a thick, rough-walled granular gas, where you might think of there being something like a gas, but where these particles are relatively large and granular rather than point particles like in the real gas or in the molecular gas. And in particular, one of the things that you might be concerned about is what are the walls of your gas look like? So if the walls are very rough, and by shearing, for example, the wall, you can provide energy to the particles within this granular gas, then the gas behaves differently than if you had a very smooth wall that can slide past the particles without imparting energy. And so one of the possible end members is this thick, rough-walled case. Another end member that I'm not going to talk about much in this talk is what's called a locally dissipated granular gas, where it's only local interactions that change the energy of each of the particles. And then I'll talk about this other end member, which is a thin flow. So for example, you can think about how thick that flow is or how thick that box is. And if it's thick versus if it's thin, you might expect there to be very different predictions of the model. So for a thin flow, but one that's also that has a rough wall, you might be able to make different sorts of predictions. And the predictions that I'm going to focus on are just two, which I think are the most important. One of the predictions is about the forcing, or about the impulses that each of these particles are impacting or producing every time they impact the wall or the ground. So you might think of the wall of the box as being the ground on the earth, and you might be interested in these forces on the ground. And those forces, or the impulses, are proportional to the forces, also proportional to the length of time that each of these forces is active. And you can think of it as being related to the mass times the change in velocity of each of the particles. So if you think about the debris flow with all those big boulders in it, every time one of those boulders hits the ground, the velocity of that boulder is changing, and depending on the mass of that boulder, a different amount of force is imparted on the ground. And that creates all these stresses that we are then interested in terms of both the erosion and the potential damage. And then the other thing that I'm going to focus on is just the number. So in terms of trying to predict how many of these impulses, how many times will the boulder hit the ground? So it's a very simple thing. You might also think of it as being how many impacts are there per unit time. And so that gives you a rate of impact. And so it's really these two things that I'm going to focus on: the amplitude of these forces and the rate of impact of these particles. Okay, so those are the two things I'll focus on, and I'm going to show you just some very approximate results for these two end-member cases that I mentioned in the previous slide. So in the rough, thick case, and in the rough but thin case, there are different predictions you can make, where I'll mention that the rough, thick case actually looks a lot like the cartoon that I drew earlier, where you might have this very thick flow here that's actually composed of particles. And the thin case on the other side, I like to make this analogy with a washboard, where you might think of the thin case as just being a set of particles that are moving down a washboard, and every time they encounter these little grooves in the washboard, they interact with the washboard, or in other words, they produce forces and go as the particles try to move down the washboard. So those are the two different end member cases that I'm going to describe. And in both of those cases, we can describe both the forces or the impulses and the rate at which those impulses happen. So I'm going to describe it very approximately here. So you could go into more details and get better approximations to this, but this hopefully will give you an idea for the basic physics that's involved, where in this rough, thick case, the impacts, the velocities of impact are related to the fluctuations in the velocity away from the mean. And you can derive a result where this fluctuation is related to the size of the particles, and it's also related to the shear rate, which is a little bit more complex, but it's related to how the velocity, the average velocity, changes with depth within that flow. So it turns out to be a very simple result. And actually the result for the rate of impacts is also fairly simple. The rate of impacts is just related to the speed of these fluctuating velocities divided by the average distance between these particles which might be colliding with each other. And so again, this is a fairly, maybe this equation is fairly obvious in terms of the rate just being related to a velocity divided by a distance scale between these particles. And then on this other hand, in this washboard type of analogy, here the impacts are related directly to the average velocity, because it's actually the average velocity is fluctuating quite significantly with every impact. And so you might think of the average velocity of these particles as changing a large fraction of the average velocity. And that means that both the fluctuating velocities and these impact velocities scale with the average velocity of the flow. And then on the other hand, the rate of impacts is related again to the average velocity, but now it's also related to the length scale between each of these ridges on the washboard. In other words, it's related to the length scale of your boundary on the ground, not necessarily related to the size of the particles or to the distance between particles like it was in the thick rough flow case. So those are the two end members that I wanted to talk about. And for reasons that I won't really get to describe here, it turns out that the washboard model is the one that's more appropriate for that debris flow movie that I showed you earlier. And it turns out that certain elements of this washboard model are also appropriate for earthquakes. It turns out that it's the impact velocities that also work out for the earthquake model, whereas the rate of impacts in the earthquake model is a little bit different from what I'm describing here. But in any case, we can apply this model and see if it makes predictions and see what how those predictions compare with what we see in the field. Now, at this point, I wanted to mention that maybe some of you are skeptical that what I've described so far, this statistical mechanics framework for understanding these processes, you might be skeptical in terms of how well this might apply to the Earth. And so we've tried to evaluate how appropriate these assumptions are in situations where we have very good observations. Now for the Earth, it's quite hard to have very good observations, but one thing that we've done is tested these ideas in a sort of lab scale, but where for us, the lab is still built into a mountainside. So I'm going to show you these examples of where we tested the model against these flume observations, where this flume is about a 100-meter flume that's built into a hillside, where the slope is about 30 degrees. And in this experiment that I'm going to show you some results for, we were able to make various types of observations. We had these geophones, which measured the ground motion. And for example, you can see some of the geophones that we had in these yellow boxes. So each of these yellow boxes is one of the geophones that is recording ground motion as the sort of synthetic debris flow is going to flow by. And we were also able to measure the flow characteristics. So I'm going to play a movie from one of the experiments that we had. And I want to note, before I play the movie, I wanted to point out that here you'll see this is the ground motion from this geophone that's off to the left of the flume. This is about 40 meters down from the whole 100 meters. And you'll see that the ground motion is displaying how the ground is shaking at that location. Okay, so I'm going to show this movie now. And initially what you see is that now the debris flow is moving downhill. It's moving down. And you can see that most of the energy being observed at that one geophone location is related to when the flow was moving past the geophone. I would say, first of all, ignore this initial pulse. That initial pulse is related to the gates of this synthetic debris flow opening. And so that's not really related to the thing that we're most interested in. And maybe I can play this again, and actually you can see a lot of complex things happening within this debris flow, but I'm really just going to focus on the amount of force, the forcing that this debris flow is producing. And the ground motions that we observe are very much related to that forcing that we're interested in. And that's why we use these geophones to observe this situation. So this is sort of just a qualitative picture for what we observed in this experiment, but we can make a quantitative comparison by comparing the ground motions observed at each of these geophone locations, where we actually had about 50 locations where we were making these observations, and compare that with the type of model that we would have from this statistical mechanics framework. And when we do that, it turns out that the theory matches reasonably well with what we observe. And so this might be a little surprising too, but if you compare, now I'm not going to describe exactly what these are, but this is basically energy as a function of frequency. And the measurements are plotted in the blue curves here for two different geophones that we had. And the predictions from the stochastic impact model are plotted in the orange line. So in this case, the blue line is here, the orange line is here. This is the theoretical prediction from this fairly simplistic model. And what I would say is that actually, surprisingly, perhaps, the theory matches the observations reasonably well, if you focus on the relatively low frequency part of this. So if you focus on only frequencies below about 200 hertz or so, and there are reasons that we think that the frequencies above that are not as well explained, but if you focus only on the regions below 200 hertz, these ground motions are relatively well explained, and these ground motions from this other station are also well explained. Turns out that all of the ground motions from the 50 different stations that we had are relatively well explained. And so this is actually what I think is fairly good confirmation that the theory that we're working on has some relevance to these types of processes that we might be interested in. And so then we can apply it to the real world and have some confidence that the theoretical model might be relevant or might be yielding useful results. So now I'm going to turn to some of those predictions that we make, and I'm going to split it between the sort of debris flow case and the earthquake case. In the debris flow case, some of the main predictions or some of the most interesting predictions are how the debris flows and the properties of those debris flows produce erosion. So at least that's one of the things that I was interested in. And so one of the predictions that we tried to make is, what is the power, the erosive power of these debris flows, and how does that scale with different features of the debris flow? And so what we found from this theoretical model is that it turns out that this erosional power is proportional to the height of the flow, but it's proportional to the velocity to the third power, and it's also proportional to the size of the particles, meaning the sort of average length scale of these boulders or these other particles within the flow, also to the third power. And because of this very high power, that means that the erosive power is strongly dependent on both the velocities and the average size of the particles, whereas it has a much lower dependence on the thickness of the flow. And it may not be clear exactly why that is, but you can get some intuition in terms of trying to understand, for example, in that thin, rough flow model that I showed earlier, that the velocities were what was causing the forces. So fluctuations in that velocity caused the forces, and the erosion power is really related to those forces, where the thickness of the flow was not so important. It was more related to the velocities and the size of those particles. So interestingly, we make some predictions. For example, if you have a flow of a constant thickness, but which is composed of very, very small particles like mud. Mud is just basically mud is a collection of water and very, very small pieces of rock that are in the sort of millimeter or smaller size range. If you have a flow that's composed of mud, it's not going to create as much damage or as much erosion in a debris flow as when you have these big boulders and when those boulders are moving very fast. And so that's one of these predictions we can make. And not only do we have this sort of qualitative prediction, but we have this quantitative one where we can compare this specific prediction of h times u cubed times d cubed with the results in the field. And I'm just going to show one comparison of that, where on this plot is plotted the average vertical forces, and these forces are related to the square root of the power. So it's a little bit confusing, but you can basically think of the vertical axis here as the square root of power. And on the horizontal axis is an estimate of the maximum size of the particles that were in a particular debris flow times the velocity of that debris flow to the 3/2 power. And so if you think about this equation that I showed you earlier, and you take the square root of this equation, and now you compare the square root of power to the square root of h times u cubed times d cubed, then you can see that this prediction would be that there's a linear relationship between the square root of power and maximum size times velocity to the 3/2 power. And that's what's plotted here. So this is maximum size times velocity to the 3/2 power. And this is the square root of erosive power. And you can see these different debris flows that were measured by this group. And the linear relationship, I would say, does a reasonable job explaining some of the scalings between these different events, although there are certainly some anomalies that we cannot explain with this simplistic model. So to some extent, I would say we succeed. To some extent, we don't quite succeed in explaining all of the observations. Okay, and then finally, I wanted to talk about the earthquake predictions. In the earthquake case, again, I didn't want to get into the details here, but basically, if you follow the same type of approach that I showed you earlier about making predictions for these debris flows, if you make that same sort of thing, but you do it for these earthquakes where the velocity fluctuations, you have a similar scaling, turns out the rate, you have a different type of scaling, then what you predict in the end is that the high frequency ground motions, the ones that are most damaging, the ones that primarily caused the building damage that I showed you in Kobe, those, if you take this stochastic model the high frequency ground motions are actually mostly determined by the geometry of these particles in terms of how large are the sort of structures within that fault zone that you're talking about, and what's the angularity of those structures. So if you have a sort of smooth but large particle, it would be different than if you have a rough large particle in terms of what these predictions are. I'm not going to go into any of the details about that, but that's a very different prediction than some of these other types of earthquake models, where in the sort of simplistic case, if you had stress building up that causes failure, in that model, it's only the stress or the amount of stress that got built up in that earthquake that produces the accelerations that are observed in nature. So there's a very different prediction in terms of whether it's the geometry of the structures or whether it's the stress building up on those structures that's that mostly causes the high frequency ground motions. Now it turns out that in the stochastic model, the low frequency predictions are very, very similar in that in this case, the low frequency ground motions are still dominantly due to the stresses that build up over that fault, but at the high frequency ground motions, it's the geometry that mostly matters. And so we make these predictions, and in this case, I'm going to show you just one example of where we think these predictions actually satisfy some observations that people have made. This particular observation that I'm going to show you is actually from a long time ago. This is from a paper by Kanamori and Anderson in 1975. But one of the things that they showed in this paper was that if you group earthquakes according to whether they have these sort of expected smooth faults or whether you expect them to have rough faults, then you get these differences between the solid circles, which are the smooth faults, and the open circles, which are the rough faults. So you can see these black filled in circles are the ones that have smoother fault surfaces, and the open circles are these ones over here, which have rougher faults. And again, I don't want to really get into the details about how this plot was constructed, but it turns out that this plot was constructed where weak ground motions are in the upper left of this plot and strong ground motions are in the lower right of this plot. And so the model, the stochastic model that I talked about, predicts that the smooth faults should end up in the upper left quadrant and the rough faults should end up in the lower right quadrant of this plot. And that's indeed, to first order, what we see here. Of course, there is other complexity which we don't understand, but at least we can predict some of the complexity that's observed. Okay, so that's the end of really what I wanted to tell you about. I've told you about how statistical mechanics can be applied to these earth processes like debris flows and earthquakes. And I've also shown you that this stochastic impact model has very significant implications for both debris flows and for earthquake damage. And if anyone wants to learn more about these things that I talked about today, I would encourage you to read these two papers that I've published recently. There's this one by Lai et al. Published in 2018, which is talking about debris flows and the model that I talked about today. And this more recent one by myself and Greg Hirth in 2020, which talks about the earthquake application. So with that, I'll open it up for questions, and let me just show the final slide, which is a list of all the references to the topics that I've talked about today. So if anyone is interested in looking at these later, you have a summary of what I talked about.
Well, thank you very much, Victor, for the very intriguing talk. So I guess people can type in their question on the chats, or